In this video, we're going to look at the movement of gas particles, and we're really going to uh, rely on kinetic molecular theory to inform what the way we think about these particles moving around. So let's start with molecular velocity and mass. Um, okay, so we said that the average kinetic energy of our particles would be proportional to temperature. So we're going to look a little bit more at this average kinetic energy idea. So I've got this equation up here. It states that the average kinetic energy of a mole of particles will depend on its mass and its velocity. So just to break down what you're seeing here a little bit more, right here we have our velocity squared. We have our mass of 1 mole of particles, and that's going to come from, so here's our mass in kilograms right here, and we need units of kilograms. And this right here, NA, is an abbreviation for Avogadro's number. And so what this NA times M really is this value that we call with just one single M. And I know there's like a million variables in chemistry with M in it. But what this is the mass of 1 mole of particles in kilograms. So it's Na times M, and this is the mass of 1 mole of particles. It's kind of a super weird C. And what this is coming from, remember, like if you've had a physics class, kinetic energy is equal to 1/2 mass times velocity squared. And so what we're looking at here is the velocity. It's going to be actually, we'll talk about this a bit more, an average velocity. We'll put this here. Times then, instead of just mass, the mass of a whole mole of particles. And so that's kind of what we're basing this on. And we see that at the same kinetic energy that's average, that a lighter particle with less mass will have a faster average velocity compared to a heavier molecule. And so what we really are saying in this statement is that our mass is inversely proportional to our average velocity squared. And so looking at this graph right here, we can see this trend. We have hydrogen, which is very light, compared to oxygen, which is heavy in comparison to hydrogen. And we have the molecular velocity right here. So that's the speed with which these particles are traveling. And here we have the relative number of molecules that have that velocity. And so we can see at the peak of these distributions, these are really their average velocities right there for the whole set. And we see with the lighter particles that we have a much broader distribution of possible velocities for our sample, but it has an overall faster velocity on average than something that's heavier, which has a much tighter distribution like the oxygen does. It's a smaller range that they have, and more of the particles will be at that average velocity as well, but it will be slower. And so this is kind of a long-winded way of saying heavy molecules are slower than lighter molecules. But there we have it. But it really comes down to the amount of kinetic energy they have on average. So now let's look at another component to velocity, which is temperature. So we see that as the temperature of a sample of gas increases, that the average kinetic energy also increases along with it. And if average kinetic energy is increasing, it means that the molecular velocity has to be increasing. And so this is where we get this idea that as temperature increases, our gas particles move faster. So here I have just a sample of just nitrogen gas, and it's at different temperatures. And we're looking at the average like the velocities of the sample of the particles in the sample versus the number of those particles. And you can see that at lower temperatures, like at 100 Kelvin, we have a narrower range of possible velocities. And our average velocity is smaller or slower than something that is at a much higher temperature. So this is looking at 1,000 Kelvin. And now we have a much faster average velocity. All of our particles, like the distribution is much broader. And so there's a larger range of possible velocities that a particle could have, but the overall average increases. So we see that as temperature increases, so does the velocity of gas particles. And we can represent this in an equation as well by combining our kinetic energy equation that we just talked about, which is 1/2 mass of 1 mole of particles times velocity squared, with another variation on kinetic energy, which is this equation that the average kinetic energy is equal to 3/2 the RT, R being that gas constant we've talked about, and T is temperature. And this is really showing that relationship between kinetic energy and temperature, that directly proportional relationship that they have. Now, the R value here is not one that has liters or millimeters of mercury in it. Instead, this one's about energy. We're talking about the relationship between temperature and energy. And we use then an R value because this is just a constant. And so it's the same value. It just now has a different set of units. And we use units that have energy in them. So remember, we're still just talking about force over area. It's 8.314 joules per mole times Kelvin. And so joules is that temperature, or sorry, that energy value or unit. Sorry. Well, combining these two equations, we get the square root of the average velocity squared. So the square root of the average velocity squared is we just abbreviate it. I don't know why. Again, into something new. We call it the root means square velocity. I'll write that out. And it's equal to the square root of 3 times our gas constant R times temperature divided by that mass of 1 mole of particles. So let's remember that this right here is the same as M, which is Na times M. And this is Avogadro's number. If you don't remember that, it's 6.022 times 10 to the 23rd times mass in kilograms. Not grams, kilograms. We need the kilograms to work with joules, right? So that way our units work out. That R value again is right here is the 8.314 joules divided by moles Kelvin. Our temperature, of course, will be in Kelvin. All right, now let's talk about mean free paths. So, kinetic molecular theory told us that our particles are going to travel in straight lines until they collide with another particle or the container wall. So we can define the path that this is taking as the mean free path. So this is just going to be a way of saying the average distance between collisions. So as a particle travels through a space, maybe it's going to travel the entire distance from one container wall to another. Before it hits anything else. And that would be the like one distance it could be. But it might hit something else and then bounce off another way and then bounce off another one before it hits the container again. So the pathways that these particles are taking will become a lot more zigzaggy the more particles it collides with. And that'll correspond with more particles being around or a smaller volume. So we define this as how it travels through the thing. And we see that the pressure will increase if that mean free path decreases. Because remember, that pressure depends on the number of collisions with the container. So if that distance that a particle travels between collisions with the container walls decreases, then it'll be able to hit the container walls more frequently. And this will increase the pressure on the system. Now, if they have a much longer path to take, or it takes more time to go from container wall to container wall, then we'll see the pressure decrease. And this might correspond with a larger volume or fewer particles that it's actually bumping into along the way. But we can build a relationship that pressure is inversely proportional to the mean free path. So that just means as pressure increases, then we see the mean free path decrease, meaning there'll be less distance between the collisions with the container walls. So these are kind of some of the foundational things that we're doing to set up kind of an understanding of how gas particles move around in space, and how quickly they move around, which impacts the pressure and the volume of the gas is occupying. So now I'd like to define two different types of movement that we can study for gas particles: diffusion and diffusion. Diffusion is when gas particles spread out from a high concentration to a low concentration. And so a gas will always expand to fill its container. And what we're showing here is two separated gases, and then we create an opening between them. And the gas that's higher concentrated, in this case, the one on the right, is at a higher concentration, so it will more quickly diffuse into the other half of the container. The red gas on the right is less concentrated, so it'll still diffuse through the whole space, but it'll happen a little bit slower. So it's still gonna move from a lower concentration of itself, or a higher concentration of itself, to no concentration, but it'll go slower than the more concentrated one. And so that diffusion is a gas particle diffusing through other gas particles. Effusion is when we have a gas that is separated from a vacuum and a hole is punched through, and we now have our gas filling a vacuum. And so in this case, effusion is, or in all cases, effusion is when gas particles are going from a high concentrated gas to zero concentration of gas, but they're not having to navigate other gas particles along the way. They're just filling in the space of the vacuum. So the rate of a diffusion and effusion of a gas are both going to be related, of course, to its velocity, to its average, or the root mean squared average velocity that we just defined. And so the faster that average velocity is, the faster a gas will effuse through a pinhole into a vacuum, or the faster a gas will diffuse to fill an entire container. So we have Graham's law of effusion next. So for two different gases that are at the same temperature, the ratio of the rates that they will move at, so the rate is speed over time, will be dependent on their masses. And so this comes back to that idea that our lighter particles will have a higher average velocity than our heavier particles. And we can set up this relationship that's described by Graham's law, where the rate of a gas, and so these rates right here mean the speed with which a gas is traveling. So it's like distance over time. So this is comparative between two different types of gases. We'll call it gas A and gas B. And we see that the rate that it travels is inversely proportional to its mass. So rate goes up as mass goes down, right? The velocity goes up as the mass goes down for a particle. And so when we compare these, we can see, I'm just going to highlight this, that we can combine this proportion into an equality. And so we can calculate the ratio, the difference, or that one particle is going to be faster than another type of particle in the gas state, by using the square root of its molar mass in kilograms divided by the molar mass in kilograms of the other one. And that's what that big M is. So it's the mass of 1 mole of particles in kilograms, right? Which is the same thing as molar mass in kilograms, right? So we would have units like kilograms per mole instead of grams per mole. So what this really tells us at the end of the day is that this is getting back to the idea that heavier gases are going to have a slower velocity. And so we expect a heavier gas to effuse slower than a lighter gas. So we'll see that the effusion rate is going to be proportional to the inverse of the square root of density. So this lowercase d here is density, which we do sometimes instead state as capital D. So density is really going to be proportional to molar mass at constant volume and number of moles of particles, right? Because if we have the same volume and the same number of particles, density increases as the mass of those particles increase, because it's that ratio between mass and volume. And so we can really connect diffusion with density of our gases. So we actually have then another version of this. We can look at effusion rates, which as either what we did before, which was where we had the molar mass in kilograms as our ratio, but we can also see it as here, a ratio of densities too. And it works in the same way. Note that again, this is an inversely proportionate relationship. And so we see the rate in the numerator corresponds with the density in the denominator of the equality, or the kilogram molar mass in the denominator of the equality. And this allows us to predict when one gas will move faster than another, like by how much more distance it'll travel in an amount of time, things like that. Which is helpful when we're just studying gas behavior in general. Though I must admit, I don't think this is a piece of introductory chemistry I ever used in the lab, but I was in a pretty synthetic lab. So let's use this in an example, and I think that will be helpful. So we're going to look at Graham's law of effusion. We're looking at water and carbon dioxide, and we have a tube that's 1 meter long. And we are going to look at it effusing through. So imagine this is a vacuum. And imagine we're going to release our sample of water and our sample of carbon dioxide at the same time on either ends of this tube that's a vacuum, and it's 1 meter long. Which one's going to travel the furthest? And how far is that carbon dioxide going to travel down the tube before it meets the water? So where on this tube are these going to meet? So let's work through this. So we're going to need to use Graham's law of effusion. So let's start by writing that down. So remember, this is going to tell us our rates relative to one another. So we're going to look at the rate of water compared to the rate of carbon dioxide. Now we know that our water has a molar mass of about 18 grams per mole, and our carbon dioxide has a molar mass of about 44 grams per mole. So our carbon dioxide is heavier, and so you can set this up either way. It's how you interpret the problem. I tend to always set this up so I have the heavier one on top. So I am going to set this up so I have the rate of my carbon dioxide on the top and the rate of my water on the bottom. Again, you could have these flipped. It doesn't matter. You'll just have a number less than 1 or a number more than 1. So looking at this, I'm going to set this then equal to the molar mass in kilograms of my water on top, because it's on the bottom here, right? So we'll put it on the top. And our carbon dioxide's on the bottom, on the top. So it'll be the molar mass of our carbon dioxide on the bottom. All right, so here's Graham's law of effusion that we're working with. So the information that we need to get a ratio is this molar mass in kilograms. And that will be able to give us the ratio between the two. Since we're going to have this travel over 1 meter, we'll use that ratio information later to get the exact distance. So what we'll do is first we're going to say that the gas that'll travel the farthest is going to be the water, because it is lighter, so it will travel faster, right? So let's write that down. H2O is lighter, therefore it will have a higher velocity, therefore it should travel further. Let's plug things in and see what that ratio actually is of how much further it will go. So I'm going to set this up again, and I'm going to do this conversion in my head. Since we're looking at kilograms, really to convert between grams and kilograms, 1 gram is equal, 1,000 grams is equal to 1 kilogram. So my, molar mass for my water is going to be 0.018 kilograms per mole, divided by my 0.044 kilograms per mole. So what I calculate for my ratio is 0.64. So what this means, let me get a little more space here. This means that CO2 will travel 0.64 times the distance H2O travels. The ratio value is going to be in the context of the one that's on the top. So we could think about this. Let's just look at it flipped. So if we did that, we would be looking at the rate of H2O relative to the rate of CO2, which would give us the square root of our 0.44 kilograms per mole. So I'm putting in the carbon dioxide now on top and our 0.018 on the bottom. So we have so right here is the mass of CO2, and this is our water. And when we plug this into our calculators, we get a value that's 1.56. And so this means that water travels 1.56 times the distance CO2 travels. So relative, whichever one you put on the top of your rate ratio is the one that you'll use that number in the context of. So water is 1.56 times CO2, or CO2 is 0.64 times water. And either one is fine. Now we know water is going to travel further. So now we can figure out that second piece, which is how far down the tube will the CO2 travel before it actually meets the water? Like at what point do these actually meet? So I'm going to get a little bit more room for this. So now, again, sorry. So let's work on the second part of this problem. How far will the CO2 actually travel down the tube before it meets the water? So we know that the water is going to travel 1.56 times further than the CO2, but what we're going to really have to do here is set up another equation. Now we know the total distance that's going to be traveled is 1 meter, or the total distance available. So that 1 meter is going to be equal to the distance traveled by the water plus the distance traveled by our carbon dioxide. And now we know that the distance that the water will travel will be equal to 1.56 times the distance traveled by the carbon dioxide from the ratio that we built right here. Now we could also write this in a different way. We could also write that the distance that the carbon dioxide travels is 0.64 times the distance that the water travels. You should reach the same answer no matter which version of this that you're using, if you looked at this from the perspective of the carbon dioxide or from the water. So I'm going to go ahead and use this one right here, because that's what I already did in my notes. And I'm going to then substitute in my distance. I've got two equations and two variables. So that's coming back to algebra. I'm going to substitute that in right here. And so my equation now looks like 1 meter is equal to 1.56 times the distance of my carbon dioxide plus the distance of my carbon dioxide. I can now combine and solve for that distance the carbon dioxide travels. So 1 meter is now equal to 2.56 distance of CO2. If I divide both sides by 2.56, the distance that the carbon dioxide travels will be equal to 1 divided by 2.1, or 1 divided by 2.56, which is going to be 0.39 meters.